All right, page 229. You did numbers 1 through 7 and some imaginary numbers. Remember, the key to working with imaginary numbers, class, is to pull out your eye. And an imaginary number, remember, is a square root of a negative. Now, they only actually gave that to you on 2 of the problems that you had for homework. The others already had the i's in there, or had part I, part non-I, part real, part imaginary. We call these numbers, anyone? Complex numbers. But number 1 was an imaginary number, I to the 35th power. And remember, we said that the key to bigger powers of I is to remember our 4 fundamental powers. Well, of course, I to the first, class, remember that was just I, because anything to the first is itself. One of the most important to remember was I squared, which is -1. I cubed just puts I squared and I to the first together, -1i. And then I to the 4th is 1. Every 4 i's is just a 1. So when we come to I to the 35th, how many sets of 4 i's are in I to the 35th, Michael? 8 different sets of 4 i's. Well, all of those are just 1, so just knock all of those out. There go 32 of your i's. How many i's are left, class? I cubed, so our answer should have been negative I. How many had that for number 1? All right, questions on that? Been a long time. All right, number 2. Pretty straightforward, as long as you remember we never really subtract in algebra class. We add the inverse. So when we add the inverse, what do we get, Maddie? -3, negative I. How many had that for number 2? All right, number 3. Here, they had square roots and negatives. So here we had to do what, Kendall? Pull out your I. So the square root of -12 initially becomes I times the square root of 12. The square root of -27 becomes I times the square root of 27. But we could also do a little bit of reducing if we felt so led. We didn't have to necessarily, I guess. 4 and 3, and then here 9 and 3. So I could take to get 2i squared of 3 times I times the square root of 3. And when I multiply the coefficients, 2i times 3i.
6i squared.
And the square root of 3 times the square root of 3 becomes the square root of, well, it becomes the square root of 9, which is just, which is just 3. And the I squared becomes -1. So our final answer comes to -18. You could have just multiplied after you pulled out the i's. You could have said I times I is I squared. 12 times 27 is 324. You like that number? 12 times 27. Get a nod from Maddie. There's your -1. And we did actually memorize at one point that the square root of 324 was 18. And there's our -18 answer. A couple different ways to do it. How many had that for number 3? Questions on number 3? Number 4. We were dividing by an imaginary number. But remember, I is what we use to represent what, Brandon?
Square root of -1.
The square root of -1, which is why I squared is -1, by the way. But I is just the square root of -1. So that means our denominator is -2 times the square root of -1. That's a radical. And you can't have a radical in the denominator. So what do we need to do here on a problem like 7 negative 6i over -2i, where there's an I in the bottom? Abby, do you remember?
Multiply everything by I.
Multiply top and bottom by an I. In the numerator, Abby, that's going to give us
7i negative 6i squared.
And in the denominator,
2i squared, -2i squared.
-2i squared. Now, here, in both cases, I squareds, class, become -1. So instead of a -6, -1, class, that's just +6. I'm going to put the +7i after it. Real always comes before imaginary. And -2 times -1, class, 2. And we could either leave our answer like this, or we could say 3 plus 7 halves I. Either answer would be appropriate. How many had one of those answers on number 4? All right, questions on that. Again, it's been a long time since we've done this. The next one was infinitely more annoying. We had a -3 plus 5i all over 15 minus I, right? Yeah, 15 minus I. And here, again, I is the square root of -1. So I've got a radical in the denominator, but I've got 2 terms. What do we do when we have a 2-term radical denominator to rationalize it, Audrey?
Multiply by the opposite. Conjugate.
Conjugate, there we go. We multiply by the conjugate of the denominator. So we're going to multiply top and bottom by.
15 plus I.
And the idea, of course, is that gives us the sum and difference down here. And to multiply sum and difference, class, 3 steps.
Square the first, square the last, square the minus sum.
So we're going to square the first. 15 squared.
225.
225. That's one we memorized at one point. Square the last, class. I squared and put a minus sign between them. In the numerator, I've got similar binomials. How am I going to multiply those, Genesis? I could double distribute, but generally similar binomials, we use FOIL. There we go. So if we multiply the first, help? Negative 45. Then I've got the outer and the inner. Now the outer's easy, Genesis, but the inner's annoying, class. Positive 75i. So back to Genesis, I combine my outer inner to get a 72i. And then we've also got our last right here. 5i times i just gives us 5i squared. But back to Audrey, in both cases, again, these I squareds become
Well, -1.
negative 1. So here, negative 1 becomes positive 1 with the 225 gives me a new denominator of 226. Here, the negative 1 and the 5 gives me a
5.
negative 5 combined with the negative 45,
-50.
negative 50, and of course we still have this positive 72i. Generally speaking, remember, we don't want a first term negative, but complex numbers is always real before imaginary. So there's one thing we could do to reduce this down. Anyone? Knock a 2 out, everything's even. So the best way to leave the answer here would be the negative 25 plus 36i all over a 113. Fact check that before I say it. Yes, and that is correct. How many had that answer? Anyone get that? Brandon did. Great job. All right, that was a challenging problem. Questions? We understand it now. Refreshing memory here. Let's see, number 6. That's pretty straightforward. We're just going to FOIL. What did you get for your answer, Maddie? Positive 1, positive 22i is correct. Anyone need to see number 6 worked out on the FOIL? Want to see that FOIL done? How many got the correct answer, 1 plus 22i? All right, those who didn't understand it from the last problem, what we should have done. All right, and then number 7, there's 2 ways we could approach it. Normally a quadratic equation, class, we want to set it equal to 0, which they already did, and then normally we want to factor, right? Backwards FOIL, if it's a trinomial, which it is. But how many realize just as you looked at it, it ain't gonna backwards FOIL? Yeah, so if you can't factor, you got 2 other options. What are they? Complete the square, or someone else? The quadratic formula. So remember the quadratic formula, say it with me. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That's one option, where we could say in this particular problem, class A is 1, B is 2, and C is 5. We could do that, nothing wrong with that. But I'm looking at this, I'm like, well, I've already got a 1 in front of the x squared. I've got an even b. It'd be pretty easy to complete the square. And that's actually something that we've been doing lately with our parabolas, was we had to complete the square. But remember, the first key is we got to get rid of the c value, the 5, right? So I'm going to kick it out as a negative 5, and then I'm going to fill in the gap. Remember, 2 steps to fill in the gap, class. Half and square. If we half and then square, and what we do to one side, now remember, in our parabolas we did opposite, right? If we put a plus 1, we had to add on a minus 1, but that's because it wasn't on opposite sides. Here we just do the same thing to both sides. This is going to turn into, class, x plus 1 squared, and then over here, negative 5, positive 1, negative 4. Then we'd have to do what, Genesis, since we got the square? Well, it's already square. There you go, square root of both sides. That's what you meant. And that's going to cancel the square to get x plus 1. And then here, what are the square roots of negative 4, class? Good, positive negative 2i. Then to finish it out, we'll move our real over as a negative. We'll lead with the real, so we have real before imaginary. And there's our answers. Negative 1 plus or minus 2i. You would get the same thing if you plugged it into the formula. How many had that? Okay, only Kendall, Brandon. Okay, anyone want to see the formula worked out? Say, I did the formula, it didn't work out for me. All right, so here, check your work. Should have been negative 2 plus or minus the square root of 4 minus 20. Is that right? Yeah, 20 all over 2a, which is 2. So far, so good. This is, of course, going to become a negative 16. And the square root of negative, pull out your I, and the square root of 16 is 4. So we should have gotten a negative 2 plus or minus 4i all over 2. And when you divide these by 2, that's where you get negative 1 plus or minus 2i. Does that make sense? All right. Questions on number 7. Good news is that's not going to be on this quarter exam. Bad news is you might see something here or there on the final exam at the end of the year. But a good refresher, if nothing else. Some of you next year pre-calculus, you'll see imaginary numbers again, though of course you'll have instruction to go with it. All right, look back across the page 228, and get the other part of your homework out. You should have had 4 systems of equations, so either 4 graph grids, or maybe if you had different colors of ink, you could use maybe 2 graph grids with a couple systems apiece. So 8 total lines that we should have drawn. I actually have graph grid today and straight edge, which is nice. Let's go ahead and review some things, though, from yesterday. We said that a single equation with 2 unknowns isn't sufficient to solve anything. Remember, we said the sum of 2 numbers is 9. Yeah, but there's an infinite number of possibilities. I said we could describe a single equation, then, class, as being indeterminate. Indeterminate. And so for that reason, I said if we got 2 unknowns, we need 2 equations. We need a set of 2 equations, or, Kendall, we need a system of 2 equations. And said we graph our 2 equations, and wherever the 2 lines or the 2 graphs intersect, there's our answer. Or, you know, some cases answers. If we have time, we'll look at one of those. We said if the system of equations, if those equations intersect each other, answers, good to go, we're happy. We describe this system, Michael, as being
Coincident.
not coincident. Abby?
Consistent.
Consistent, the other C one. Consistent. A consistent system, we get an intersection, right? We get consistent. You think consistency, okay, would be, you know, maybe you think of an adult, you know, always reacting the same way to something, okay? Like, you know, Genesis is like, hey, Mr. Dasky, can I eat cookies in algebra class? I'm like, sure, Genesis, whatever you want to do. You're my favorite. And then Audrey's like, Mr. Dasky, can I eat cookies? No! That's inconsistent, right? That's going to breed strife and contentment and resentment. I didn't give you permission, for the record, to eat cookies in my class. And Calvin's like, I can eat cookies in class. Anyway, all right, so, but a consistent would be, no, you can't have cookies. Can I? No, you can't have cookies. No, nobody. That's consistent, right? One answer, right? One point of intersection. Well, if it's linear, I guess. But if the lines never intersect, the graphs never intersect, we don't get any answers, then we would describe the system, back to Michael, as being
Coincident.
Audrey. Michael, Brandon, whatever your name is. Hey, you. Inconsistent. So consistent, class, the graphs intersect. Inconsistent, they don't intersect. Now, in the case of lines, what would keep lines from intersecting? Only if they are parallel, right? What would be the answer to an inconsistent system since they never intersect, class? No solution. No, okay? Now, there is a possibility that when we draw our 2 equations, draw one equation, and then our next equation is right on top of it. How would we describe lines that are one on top of the other? Go.
Coincident.
Coincident, right. So if we have coincident graphs, that means the one line is on top of the other. How many times do they intersect, class? Infinite number of times. How are you supposed to figure out the answer? You can't. The answer there would be indeterminate still, right? Because you have infinite solutions. All right, so dependent equations will coincide. Coincident equations are dependent equations. What you're looking for is independent equations. They don't coincide and hopefully intersect. Let's see how you did on the homework. Page 228, you had numbers 1, 2, 7, and 8. And different ways we could graph these linear equations you were given. My thought would be usually slope-intercept form, but I don't suppose you had to. For instance, number 1, if you wanted to do the intercept method, plug in 0 for x, plug in 0 for y, so as to get your intercepts, you could do that. How did you graph your first equation on number 1? Hey, you. I know, Brandon. I started to say Brandon, then I caught myself. No, it's Mike. No, it's Brandon. Whatever your name is. You. I'm sorry? You did the slope intercept form? All right. And so what did it look like when you got it in slope intercept?
Y equals negative 3x positive 9.
Well, negative y would equal negative 3x positive 9. So y would equal...
Y equals 3x negative.
There we go. We put the 3 over 1. So we're going to plot our y-intercept at, let's see, negative 9 is down here. Rise 3, run 1, and use straight edge. And should have line like so. All right, and then Abby, for the next equation, how did you graph this one?
Slope intercept form.
All right, so you had
Y equals 1. Which one is that? Oh.
number 1, the second equation.
Negative 1/2 x plus 5.
There we go. Should have come out to a negative half x plus 5. Move the x over as a negative, divide everything by 2. And so here we've got our intercept at 5. And we're going to rise 1, run backward 2. And when we connect the dots here... Now, they don't intersect perfectly at a point. And it's possible that my lines just got a little bit off. So it looks like we're almost like at 3.5, 3. That doesn't sound right. No, that's not going to work out to be 3.5, 3. Maybe it's supposed to be over here. Maybe this is supposed to be the point right here where they intersect. Maybe it's supposed to be 4, 3. Yeah, 4, 3 would work. Do you see how the graphing method, even if you miss a little bit, because you're inaccurate, you at least kind of know the ballpark here. How many got exactly 4, 3? It was right on. Your graph was better than mine. Show offs. All right, questions? Any questions on graphing number 1? All right, I'd like to look at number 2 here, where we had a 5x minus 2y equals negative 6. Yes. And then x plus 4y equals 12. And yes. All right. Audrey, top equation. How did you do it?
I did slope intercept.
Good. This one definitely want to do it that way. So what does it become when you go to slope intercept form?
Y equals 5/2 x plus 3.
Y equals a 5/2 x positive 3. So let me switch to a little bit of pink chalk I have left here. Starting at the 3, we're going to rise 5, run forward 2. And first equation should look like that. All right, and then write the next equation, Genesis. How do we do this one? Okay, to get... And then to get
Y equals negative 4 and 4 plus 3.
There we go. And so now, well, this makes it easy. There's its y-intercept, right? And yeah, you rise 1, run backward 4, but even without graphing, I already see the point of intersection. It's actually intersect right on the intercept. And so obviously the answer to your class is 0, 3. That was not hard at all. I saw that before I drew the line. How many got 0, 3 for this one? All right, questions?
I had a 5/2 x negative 3.
Oh, so when you divided the negative 2, or did you double switch, or did you move the 5x?
I moved it over, but at the same time multiplied everything by negative.
Right, so you move it over to negative 5, and then you change all the signs, and there goes that one. Okay, all right, good. Any other questions, comments on the first 2?
Mine intersected perfectly for that one, and I got it right on 3.
Right on 3, 0, 3?
Mm-hmm.
Great job, me too. Well, kind of. I was a little more accurate. Okay, let's go ahead and take a look at numbers 7 and 8 now. Numbers 7 and 8. And let's see, we've got 3x plus 2y equals 12. And we've got a negative 9x, negative 6y equals negative 36. All right, top equation. How did you do it, Michael? Intercepts or slope intercept form?
Slope intercept form.
Okay, so you got
Y equals negative 3/2 x plus 6.
Good. 3/2 x plus 6. And be lazy because I don't want to draw a new graph here. I'm just going to erase all the old equations. All right. My laziness knows few limits. All right, so we're at the 6. Rise 3, run backward 2. Should have had a line like that-ish. And then for the next one, Kendall, what do we do with this guy?
Select intercept.
Okay.
You get negative 6y equals 9x negative 6 and divide by negative 6. To get y equals negative 3 halves x plus 6.
And wait a second. Thoughts, class? Yeah, it's going to be a coincident line. We would describe these equations, class, as being... Well, the solution is, but the equations themselves are said to be dependent equations. The graphs are coincident, the equations are dependent, and the answer is indeterminate. The solution is indeterminate. There are too many answers to this particular problem. Everything's a correct answer. All right, well, everything along the line. We're going to talk about that in our next lesson. How many have the indeterminate solution here? All right, good. And then on the next one, I'm going to use up a whole lot of space. Numero 8, we have a book back here. 15x negative 6y equals 30, and a 20x negative 8y equals 40. Maddie, top equation. Y equals, let's see, that makes it you said 5 halves x, okay, and then you said negative 5. All right, good job. All right, so we've got our negative 5, rise 5, run 2. And could have an intercept method, we've got the same thing. And there's that equation. And then, we probably should have done that in pink. Then this one, what do we get for this? Back to Brandon.
The same thing.
Yeah, the same thing. Move the 20x over as a negative. We divide by the 8. You're going to still get that 5 halves, so you're still going to get that negative 5. So again, class, we have what kind of equations? Dependent. It is a consistent system. They do intersect, but they intersect everywhere. So it's a dependent system, coincident graphs, and a solution that is indeterminate. So many terms to keep up with. All right, questions on the homework. All right, at your seats, I want you to set up a new Cartesian plane. I'll even set up a new one, suffer with you. And go ahead and graph this system of equations. 3x plus y equals 5, and 3x plus 3y equals 7. Once you finish the first one, go ahead and graph the next one. on the first system of equations, it looks like it's really close to 1, 1. But 1, 1 don't check. If I try to be more exact, it looks like it's like maybe 1 1/4, or maybe because of the 3's 1 1/3, 1. 1 1/3, 1 does check. How many figured out it's 1 1/3 or 4/3, 1? How many put down 1, 1 because it was really close? How many didn't graph the equations? Questions on the first one?
I had 1
1.5, 1. Okay, that was also would not check, but it's really close. Questions on this? Questions, comments? Yuck. Okay, pink one. Thoughts on the pink system? Parallel lines. So how would we describe this system since these lines don't intersect? It's an inconsistent system. What's the answer? No solution. They just don't intersect. Questions on these? Questions? How many are kind of fed up with this one? Yeah, me too. Graphing, I mean, I've already been inaccurate a couple times with my graphs just not being perfectly precise, right? And then on top of that, here, I mean, how am I supposed to know 1 1/3? I mean, other than, I'm pretty good with numbers, so I figured out, okay, 1 1 puts me at 4, 1 1 puts me at 6, I'm just a little off. An extra third more would do it, right? From each of these 3 x's. So I kind of figured it out that way, but that's annoying. There's got to be a better, easier way, right? I mean, after all, mathematicians are lazy. There's got to be a better way. And there is. So, under solving systems of equations, method number 2, Roman numeral 2 in your notes. Let's forget this graphing nonsense. Let's move on to something, number 1, more accurate, right? Where if it's 1 1/3, 1, I actually get that. And number 2, easier. I don't like setting up Cartesian planes. I'm lazy. Method number 2 is called the addition method, or sometimes called the elimination method. So solving systems of equations, Roman numeral 2, Roman numeral 1, remember, was graphing. Roman numeral 2, using the addition or elimination method. Either name, I want you to be familiar with both. First key, though, in order to use the addition method, which is so called because you're going to do some addition, also called the elimination method because you're going to eliminate stuff. That's always fun. First key, you have to have like terms. You must have like terms. Now, in the case of what we've been doing, we've been working with linear systems. What do linear equations have? X to the first and y to the first, right? Those are going to be like terms. So oftentimes these are this method is used for a linear system. Now, we will get into what are called quadratic systems, where one or more of the equations in the system are quadratic equations. And there's actually various forms of quadratics that we'll get into. Okay, but the addition or elimination method. Let's go back to that same one we used a minute ago. I'm going to put it back down here. You can put this in your notes. 3x plus y equals 5, and the 3x plus 3y equals 7. Well, step number 1 is to line up like terms. Step number 1 is to line up like terms. You have to have like terms to use the method. You have to line up the like terms as your first step, which a lot of times this will be done for you. Here it certainly was, right? Already lined up for you. Step number 2, you're going to pick a variable to eliminate. Step number 2, pick a variable, x or y, to eliminate. Hence the name Elimination Method. Pick a variable to eliminate. Now, under number 2, a couple of things. I'm going to pick the 3x to eliminate because there's 2 requirements on what you're going to get rid of. The 2 variables must have the same number, and they also must have opposite signs. You must get the same number for your variable, and you must get opposite signs. Well, I already have the same number, but I ain't got opposite signs. I got 3x and a 3x. They match in number, but they have the same signs. You know what I'm going to do? Change all the signs in my top equation. One of the equations, just change all your signs potentially. All right, so as you're doing this with me, change all those signs. And now, step number 3, add the equations together. Step number 3, add the equations together. By getting same number and opposite signs, that's another way of saying you're getting inverses. And when you add inverses, class, what happens when you add inverses, class? Cancel. Gone. Boom. Eliminated, right? Elimination method. Notice I added to do that. Hence addition method, right? Either name. But I also have to add the y's together. Well, I've got a negative y now and a 3y. 2y. I've got a negative 5 and I got a 7. 2. And so y equals 1. Step number 4, solve for the remaining variable, which is kind of a natural process. As soon as you got 2y equals 2, you're like, oh, I'll solve for y, right? So you all kind of knew step 4 intuitively, solve for the remaining variable. And there's the ordinate, which we had last time. We knew the ordinate was 1. It was just, what's the x? Is it 1, 1.5, 1/3? What is that? 1.25? All right. We've got the ordinate. I'm still missing the abscissa. So for step 5, we're going to go back to one of our original equations. I haven't messed up this one yet. So I'm going to go with the 3x plus 3y equals 7, but plug the variable back in. So step number 5, plug the answer into one of the original. I'm going to go back to my lower equation. So instead of 3x plus 3y equals 7, it's going to be 3x plus 3 times 1 equals 7. Plug the first answer in to one of the original equations. And you can probably guess what we're going to do next. Solve for x. Yeah, solve for the other variable. Solve for the previously eliminated variable. 3 times 1, class. 3. Subtract the 3 from both sides to get 3x equals 4. And when you divide away the 3, we end up getting the 4/3, or the 1 1/3. And look at how little work I had to do. Change signs. Cancel. 2y equals 2y is 1. Boom. Plug in a 1. X is 4/3. We're done. No Cartesian plane, no nothing, super easy. I cross my fingers when I ask this. How many remember doing this in the years past now? Okay, all right. So Abby and Michael remembers this now. Okay, so we got one more person who remembers this. Write this down. 3x plus 2y equals 7. 2y negative x equals 3. 3x plus 2y equals 7, 2y negative x equals 3. I told you step number 1 is to, looking at your notes, line up like terms. Do I got like terms lined up? No. Generally, you're going to want the form x, y equals number. Not always, but generally, you want that x, y equals number. So I'm going to leave the top as it is, but I'm going to flip-flop the lower equation. Make it say negative x. Make sure you keep the sign with the term. Positive 2y equals 3. And now they're lined up. Step number 2. Pick a variable to eliminate. Do I want to get rid of the x, or do I want to get rid of the y? Maddie? the x. Now the advantage of choosing x, do you notice the signs are already different? But they don't have the same number. This has a 3, this has a 1. But class, if I multiply the bottom equation by a 3 all the way through, just as we've knocked 3's out of equations in the past year, I'm putting a 3 into everything, multiplying everything by 3. What does this lower equation become now, Maddie? And do you see that now, these two equations, if I add them, the x's, class, will cancel. So let's go and add them. Cancel off those 3x's. What do I get when I add the y's now? 8y equals, and add the constants, 16. Class, thoughts? Y equals 2. So there is the ordinate. But I need the ordinate and I need the abscissa. How do I go about getting the x value here? Genesis? Good, I'm going to put this 2 that I got for y into one of my originals. Now, I've messed with this equation so much, I'm going to just go right here. And instead of the y, I'm going to put 2. 2 times 2, class. Subtract it away. Divide away the 3. Boom, done. So much faster and easier than the graphing method, right? So if I have the choice, I'm never graphing. Hate graphing. Too lazy. Write this one down. 4x. Oh, real quick note before we write down this next one. Did you notice the 2 y's were already 2 y's? How many were thinking you wanted to get rid of the y? All we would have had to do is change the signs. Instead of multiply 3, just change the sign, or signs here, right? And that would have canceled here. Would have given us a 4x equals 4. There's our x equals 1. Would have plugged that in and get y equals 2. So there isn't a wrong choice there. Just whatever you feel is easiest. Write this down. 4x plus 3y equals 17, and 2x negative y is equal to 11. 4x plus 3y equals 17, 2x minus y equals 11. All right. Step number 1, class, is to line them up. Thoughts? I already lined up. Yay, that's happy. All right, step number 2 is to pick a variable to eliminate, x or y. Brandon, since I keep getting your name wrong, I'll let you pick. We're going to get rid of the y. Upside of the y, they already have opposite signs, right? But they don't have matching numbers. So to get them to have matching numbers, what would I need to do, Audrey? Good. Take the bottom equation and multiply all of it by a 3. So that my bottom equation is going to become
6x minus 3y equals 23.
And now my 3y and negative 3y line up. I'm ready, class, to do what to the two equations? Add them. And when I add them, the x becomes 10x. You're doing this with me. The y's cancel. And over here, 17 and 33 gives me 50. Well, you solve for x in your head. Now x is 5. And there's my abscissa. What do I need to do to get the ordinate, Kendall?
We'll go back to the original equation and plug it in.
All right, where do you want to plug it in?
The 4x plus 3y.
And make sure you put it in for the correct letter. X is 5. Don't go put it in for the y, put it in for the x. 4 times 5, class. Subtract away the 20. Negative 3. Divide away the 3 from the negative 3. Negative 1. And there we go. How many of you, when Brandon said he wanted to get rid of the y, how many are thinking, I'd like to get rid of the x? What would I have had to do to get rid of the x here, class? Bottom by a 2, which would have given me a 4, and then one of the two equations, probably the bottom, change those signs. And that could have given us the same answer. We just would have gotten the negative 1 first, then the 5. Questions on this? Turn your textbooks to page 235. Page 235, I want you to do numbers 1 and 3. Numbers 1 and 3. Not graphing, but use the addition method or the elimination method. 8, 6 for number 1. 8, 6 for number 1. All right. And how many of you on number 3 got as far as your maybe your ordinate, for instance, and are like, oh my. Yeah. Strategy tip. All right, you could plug this into your calculator, times 9. You could make it a negative and add it to 20, or do 20 minus whatever you got, and that would give you your x. You could do that. Or if you're like me and I'm too lazy to walk over there and get my calculator, you could say, well, I got the y by knocking out the x. So instead of even touching that ugly, hideous fraction, I'm going to now turn around and resolve it, but this time get rid of the y. Watching. What would I have to do to make these y's match? Because 9 and 6 don't match.
Multiply 9 by 2/3.
If I multiplied the 9, hold on, by a 2, and I multiply the bottom by a 3, I could make them both become the number 18. A little bit of outside the box thinking, I suppose. Distribute a 2 through the top class.
2 plus 42
And take a 3 all the way through the bottom.
42.
Negative 42. We'll knock out the y's, leaves us with 5x equals negative 2. I got a negative 2/5. Now, how many of you already plugged it in and got the negative 2/5? Right? It's the same answer. It's just whether or not you want to do it on the calculator and wonder if you might have had a keystroke error. Or, I'll just solve it a second time and knock the y's out this time. Do you see what we did? 9 and 6 don't cancel, but I can turn them both into 18 and make them cancel. I could have done the same thing here. Now I wouldn't, because the y's canceled so well. I could have turned 4 and 3 class both into 12. Top by 4, bottom by 3. Does that make sense? So something we could have done. I want you to do numbers 6 and 8 now. 6 and 8. I'm going to let you choose your poison on 6 and 8. They're going to work out weird. Again, but aren't you glad you don't have to figure it out from a graph? Like, is there any way I would have gotten negative 2/5, positive 2 and 4/15 from a graph? Never. Graphing's so much less accurate. And in many cases, so much more of a pain. Not all pain is gain. The other upside of doing it this way is if you screw up this answer, you still have a chance at the next answer. You screw up your first answer and plug it in, you're doomed to get both parts wrong. Once you're done with 6, check your answer. If you're good, move on to 8. If you're not good, either figure it out or ask a question. If you're good with 6, move on to 8. If you're not good, figure it out or ask a question. aren't you thankful for scientific calculators that can do fractions if you want them to? Yes, ma'am.
Where did you get the 63?
Right here, remember I multiplied a 2 to get a negative 18 up here, and 81 adds together for 63.
Okay.
Did you forget to take the 2 all the way to the negative 9?
Yeah.
Common mistake. Let me emphasize what Abby did, not to embarrass her, but to serve as a warning to all of us, because this is probably the most common mistake I see with systems. When students have to multiply the 2 or maybe the 9 and the 2, they are good with the first numbers, but for some reason they forget after the equal sign, this has to be multiplied by 9 as well, or this has to be multiplied by 2 as well. This had to be multiplied by 2 as well, right? So make sure we multiply everything by that number, including the other side of the equal sign. Good. Done with 8 as well? Any other questions on 6 before we wrap? All right, the good news. Your homework works out a lot better than these crazy ones do. So we did the crazy ones in class. Your homework would be a lot better for you. All right. By the way, real quick, answer to number 8, in case you were able to finish. We had a couple people finish it. 13/12, 23/16. I got a couple nods from folks. Excellent. All right. Homework for this evening is to do page 235, numbers 2, 4, 5, and 7. Page 235, numbers 2, 4, 5, and 7. Also, study pages 233 to 234, the example problems. Page 233 to 234, the examples. And talk about some things in our next lesson on Tuesday when we come back after our 3-day weekend that I want to make sure you have a chance to see before I have to teach it to you. All right, have a wonderful rest of your day and a wonderful 3-day weekend, and you are dismissed.